No. Do you want to talk about water? Let's do it. Let's talk about water. So we're going to talk about water today. I think I talked about it last time a little bit. And then, there we go. Let's talk about water, and then I'll take a bunch of questions. We'll see how far we get today. Should be pretty fun. I brought some widgets too. So what is your experience with water? I'll just start off this way. I think a lot of us, including our visitors over here from the Robotics Club, probably have seen something like this. Do you guys know what this is called? What's the technical term for it? The water cycle, right? It's something that spins around. Water moves around, but as human beings, we've figured out a way to harness that. And that's kind of what the point of today. Like, I did a lot of my research before in remote mountain basins, and then I just discovered that I like cities. Therefore, I didn't create a class about mountain basins. But anyway, essentially, we're going to talk about cities today. And we're going to start off by catching everybody up on the various kind of water systems that exist in cities. So what I'll do is basically zoom into a city. And what you'll see very quickly, these lines represent all sorts of water infrastructure that moves water around, okay? And there are different kinds of water. But even if you take a city like Ann Arbor, which has, let's say, 100,000 people, even relatively small communities in the United States are underpinned by hundreds and hundreds of linear miles of water infrastructure. And that infrastructure moves water around. And it turns out it's not okay to just say, here's water. You want to basically talk about what kind of water we have. So what I'll start off with is just my classic water icon. So from there on, this is what I'm referring to as water. And I will argue that all of you have experienced this water that I was showing in the prior diagram. So when I say water that you interact with on a daily basis, what's one of the first things that comes to mind? Drinking water, yeah, because yeah, you need it, right? So here's drinking water. Here's like my icon for that. Drinking water. It turns out we don't just take that drinking water from the river. We actually have to treat it. So we tend to put stuff in between, right? Unless you like drinking river water. We put these treatment plants in place that basically take the water and clean it. And we have another special guest, Professor Raskin over here. Can you raise your hand and show everybody? She's one of the world experts, major experts in drinking water systems. So if you have questions, you can talk to her after class about this. So there's drinking water. Okay, what else comes to mind? We all do it. Yeah. Sewage, yeah. So when you flush a toilet, it's got to go somewhere. It used to just go to the river, which is represented here, but now we also know we should treat it, so that's what we do. Like, in the past century, we kind of figured out, let's treat that water before we send it down, because, we're going to drink it again. So, okay, this is my second type of water. What's another kind of water? This is the forgotten one oftentimes. Somebody say stormwater? Cool, yeah. So that's pretty good. Usually that one doesn't come up. But there's stormwater. So all of our roads and highways and everything else that basically lives in a city, when it rains on top of that, that stuff's got to go somewhere. And so there's a special kind of infrastructure that conveys that. And what I'd like to do is kind of step through each one of these and show you where we are with this in the United States, and then I'll pick one of these to just discuss today with you. So let's talk about drinking water. So obviously that always comes to mind first, and it comes to mind first because we interact with it very kind of intimately, right? We drink it. Turns out that infrastructure in the United States is quite old. In a lot of cities, 100 years, over 100 years, and a lot of these pipes are bursting, right? So it's not uncommon that you go to a city like New York or whatever, and you see leaky pipes, you find them. By a lot of estimates, depending on where you live in the United States, you can lose up to as much as 20% of water due to leaks. And that kind of sounds crazy, right? Like you're losing 20% of the water. That's not just lost water, that's lost energy that you use to move it. Because for a lot of cities, at the end of the month, one of the biggest energy bills is actually the energy associated with turning pumps on and off to move water around, right? So that's just water loss. We've also seen water in the news for a variety of things. We don't need to go into detail here, but basically like a local issue here, if you will, in the state was Flint, Michigan. And it was an example of what happens when water systems aren't maintained to residents' expectations, and that's when you have politicians show up and drink the water to convince you that it's safe, which even throws me off sometimes. Like, I don't know, what are you trying to get me to do? Okay, so that's drinking water. Let's talk about sewers. Here's my favorite picture of a sewer. This is an example of when invisible infrastructure becomes visible. This is in Taiwan, I think. This sewer pipe basically blocked up, because believe it or not, flushable wipes are not flushable, okay? Take that home with you. Because they clog stuff up, then you have all this methane gas, and all these gases build up, and something lights it, and all of a sudden, people know that sewers exist, okay? So infrastructure is so old, so much so that it's exploding, okay? So that's that one. The one I'll focus on today is actually stormwater infrastructure. It's the one that I work on, and I always call it the forgotten one, because the other ones I think sometimes get a little bit more attention. But basically, you interact with this on a day-to-day basis too, because you'll be walking down the street and you'll just be like, ew, like what is that, right? This is what it looks like. It's a gutter, right? What do these gutters do? we don't like standing water in our cities, right? Like as human beings, we like nice, neat environments without puddles. So what we do is we build these gutters in, and these gutters feed into other systems. They feed into pipes, they feed into bigger pipes and channels, and they ultimately end up in the river still. And we've done such a good job building them that they're basically tearing up our ecosystems right now. But the good news is we don't have as many puddles in streets, right? The engineering is working. Lots of issues with this stuff. So if we look at California, for example, so this is the city of LA's stormwater system, okay? It's famous because of movies where people race around in it and they skate in it or whatever they do. But basically, the engineers back in the day were told, we don't want standing water, so get it out as fast as possible, okay? And they did that. They engineered a system that's quite amazing. When it rains in California in the summer, when you get one of the rainstorms, 10 billion gallons of water are flushed to the Pacific Ocean without about an hour and a half. Okay? That is a massive amount of water, and it's a large chunk of their annual use, right? So California is always in the news about we don't have enough water, well, they're flushing it out. And now they really wish they could keep it, but they told the engineers back in the day, like, get it out. Okay? And while some parts of the country are struggling with this drought-type stuff, other parts of the country, like in the Midwest where we are struggling with just crazy, crazy flooding and stuff. I just like this picture. I think this is somewhere in Wisconsin. Especially, don't do this, kids. This is extremely dangerous, okay? This is just a person kind of casually staring into this, this interesting-looking thing. But it turns out that flooding is extremely dangerous. In fact, flooding is the leading cause of natural disaster fatalities in the United States. And it's not like the kind of river flooding you would think of. It's actually people kind of misjudging how much water is under highway overpasses. Little innocuous stuff like that. Because it turns out that when you don't know how much water there is underneath a little overpass like that, and these are pictures from Detroit actually, and that's the one I found somewhere else online, your car is full of air and it's basically a balloon. So when you go into a puddle, and if that puddle is big enough basically, your car will float up and flip over. Okay? So that's like the PSA today, don't do that. It doesn't matter how shallow it looks, you have no clue how buoyant your car becomes and stuff like this. And it's a crazily preventable kind of thing, and believe it or not, this is like a leading cause of as I said, natural disasters, fatalities associated with natural disasters. So that's flooding. Flooding is obviously a big issue, but so are environmental concerns with stormwater. So as I was telling you earlier, this stuff has to go somewhere, and it goes to our lakes and it goes to our rivers, right? We do not treat our stormwater in a lot of cases, and in some cities, the stormwater is actually combined with the sewers. So this is a picture of beautiful Lake Michigan, and what's washing into it is this poop. It's just basically wastewater, right? It's your toilet water that mixes with storm water, and then when they can't handle the capacity, it basically just washes off into Lake Michigan or any kind of other lakes or rivers, and it leads to images like this. So, when you search for Lake Erie on Google Images, which maybe my feed is contaminated now, but basically you don't get pictures of beautiful lakes, you get pictures of dead fish and other kind of stuff, right? Because all these nutrients and other things that are inside our stormwater and our wastewater are basically, they're letting this algae thrive, and this algae is killing a lot of stuff. And you just read the news. It's not just here in the Midwest, but it's all over the East Coast and a bunch of the West Coast. So that's a problem, right? That's not good. Okay. So what I want to focus this talk on today is when you have something this bad, like Lake Erie that's polluted by algae blooms, and you want to have something like this where if somebody goes on Google Images and says Lake Erie, you want to get a picture of a beautiful beach, how do you get there? Right? And there's many ways to get there. So, as an engineer, what I'm taught and what I teach students is, you have something, you want something, just do something about it, okay? This is my part of making a talk accessible, okay? You do something. What do you do? Okay, here's the how cities work part of all of this. So, what do we do about stormwater? This is the sort of pictorial representation of a city, a community, doesn't matter where it is. It's sunny, but then it rains. And when it rains, you're gonna get flooding, right? So, okay. Perfect, good. Everybody on board? Okay, you're gonna get flooding. So what do? We're like, we don't want flooding. Let's build a pipe, and let's put that water somewhere. And where are we gonna put it? And for the sake of, just simplicity, we're gonna put it in the big bucket. That's what we're gonna do, okay? Seems kind of simple, but it turns out that's exactly what we do. So here's what a big bucket looks like, okay? So you solve this bucket, it's like, cool, we solve problems, and the way we solve problems, big problems are solved through big solutions. So does anybody recognize where this is? Chicago, okay? A few people recognize it. Obviously, our civil engineers know these things. This is underground. This is one of the largest storage tunnels in the world. It's a $12 billion project, as I actually learned yesterday. And essentially what it is you go to where you have flooding and you dig a big hole. there's your bucket, and then you just put a bunch of water in it. And we've been solving problems like this for a very long time. I mean, the Romans did it, okay? This is just a more sophisticated version, and technologies have evolved, but this is the kind of stuff that made me want to become an engineer. I was like, I want to build big stuff like this. I mean, look at it. People go in and take selfies. Like, I guess it's sort of cool, right? So that's great. The problem, though, is that not every community in the United States has $12 billion, right? Big buckets are really expensive. So if you don't have money for a big bucket, what can you do? Put it in the river, huh? What is the amount of water? Let's say it's a billion gallons. Yeah, put a bunch of little buckets. So it's classic kind of, I'm telling you, this is how it works. You want to know how cities work? This is how it works. If you don't have money for a big bucket, you pay for a bunch of smaller buckets. Every year, build a new one. And that's the state of American infrastructure. Unlike many other forms of science and engineering and things that we build, we don't have the luxury to dig up everything that was built 100 years ago and fix it. So we fix one little piece at a time. So a little bucket is not, it's a small part, but you've seen this. It's in your neighborhood. So here's one on the left that it's called a stormwater pond or a detention basin. The one on the left doesn't look as nice. They make them look nice in parks and stuff like that. But when you look at these, they're not aesthetic features. They're actually mandated by the city. They're little buckets that are supposed to catch all this water. Okay? And this is known as gray infrastructure. Okay? That's why I represent by these gray buckets, because you're just digging out little holes, right? That's what you're doing. So people came around and they said, well, I don't like gray infrastructure. I want something more natural. Okay, this is, again, my representation of it. Why don't we make it green? Okay, so that's what they did. They just took the stuff and made it green, okay? What is this? And they called it green infrastructure. The idea that you're going to replace many of these small gray assets, or potentially these big storage tanks, with many small things that will take that water, they'll infiltrate it, they'll capture it on the road, and it's really pretty because it's green, and that sounds great. And this is a huge fad now, and not fad, like this is a huge, huge thing now in the stormwater community, and a lot of people are working on this, okay? So what is this supposed to do, these buckets? Let's take a parking lot. God forbid we need parking lots. I mean, as an engineer, I still think they're useful, okay? But we don't like them from a water perspective, and why is that? So let's say it rains in a parking lot. What's going to happen? This is the only plot I'll give you, and this is the only thing, like if you want to pay attention for 30 seconds now, this is the thing I'll plot and kind of explain it. When it rains on anything, but specifically a parking lot, what's going to happen is the water levels are going to go up, and they're going to go down. That's what I'm plotting. Okay, so during a storm, water goes up and it goes down. And we joke a lot of times when we teach water resource classes, water flows downhill. Yeah, that's what it does. That's the physics of water. But anyway, during a storm, the water level is going to go up and it's going to go down. And if it goes up too high, you get a flood, right? So what we're going to do is we're going to put these green things into place, for example, right? Because what that's going to do is it's going to capture some of that water. It's going to slow it down because it's not just going down as fast parking lot. It's being captured by plants. It's being treated. But ultimately, you get something that looks better. Okay? Now, it's up to you to decide, does this look better to you or not? But essentially, the state of art, and this is what we try to do as water resource engineers, we try to look at these things called hydrographs. It's a graph of hydro, okay, water, a plot of water, and we try to get it to look less spiky and more flat, okay, because more flat is somehow better, right? And so that's what we try to do, okay? So that's what we do. It's great. Okay, we're going to do stuff. So this is the part of the talk that I like to call the dangers of doing. Okay? We're going to focus on this specifically. And what I'll do is I'll zoom into a place that you know, City of Ann Arbor. So here we are, University of Michigan, logo. Even a place like Ann Arbor, with a relatively large tax base, and how do I know that? Because I pay the taxes. Really affluent town that, relatively speaking, has a decent amount of money, suffers from issues like this, right? It suffers from flooding and it suffers from water quality impairments. So they do what other places do, is they build stuff, they do stuff, right? That's what we want to do. We have problems, we want to solve them. So many of these distributed things. So when you're driving through the city from today on, you see these things, you can go, oh, it's a bunch of little buckets. They're just capturing water and they're trying to treat it and they're doing a bunch of other stuff. So what I'm going to do is I'm going to zoom into something called a watershed. So this is a map of Ann Arbor, and what I've done is I've zoomed into basically the southern portion of it. For your reference, this is my reference. This is Costco down here, okay? This is that cool pointer. It's free samples. Okay, but anyway, we're up on North Campus, and this is about 10 square miles. And when water flows into the system, it goes towards the Huron River. And what the city did is to mitigate flooding and mitigate these issues that they have there with stream erosion and a bunch of other things is they start installing stuff. And this is conceptual. This is not the real images from it, but it just goes, okay, you have a problem in this neighborhood, let's solve it. A problem in this neighborhood, let's solve it. One little bucket, another little bucket, and just put these buckets around. Okay? Because when water flows into this thing, we're going to slow it down and we're going to do good. And the question that we had in our lab was, does doing good, if you will, at a bunch of little places add up to doing good at the larger scale? okay? It seems intuitive that how could it not? How could you not, fix one neighborhood, fix another neighborhood, which is how we fix water in the United States, would somehow add up to a bigger fix? Here's an example of what could happen. So let's say I'm going to zoom into these two neighborhoods right here, okay? And what I'm going to plot again is that hydrograph. It's the plot of water over time. And let's say it rains now on top of this area. So it rains in one neighborhood, and you're going to get, water goes up, water goes down, okay? Another neighborhood, water goes up, water goes down. But now they're flowing together to a downstream location near the river, okay? Another neighborhood, okay? They're going to add up to look a certain way. So I'm going to say here that if you add up the one over there and then you add up the red one, you're going to get that downstream behavior. And now it's the budget year, and we're going to say, okay, we're going to fix this watershed. We're going to go in and fix a bunch of stuff. So what we're going to do is we're going to go in this neighborhood number 1 and say, okay, look, we fixed that one. We installed something. We're going to fix another one, and we're going to install something. But now if you're not paying attention to the bigger picture, the system, what might happen is they add up now together, whereas before they didn't add up. And that leads you to a really kind of a strange scenario where not only is good plus good not good, it could be worse. Right? So it could be, I'm not saying this is the case, but this is the academic in me kind of prodding out there saying that we're going around fixing things, thinking that we're improving everything, but we could be making things worse. And we're investing millions and millions and billions of dollars in infrastructure doing this. So this is like the geez, Rick moment here, like geez, what are we supposed to do here, okay? There's many things, and this is not necessarily what happens all the time, but it could happen, okay? So what is the solution? So one solution that kind of motivates us in lab it's kind of given by this guy right here. I'm segueing here a little bit, but does anybody recognize who this is? Ah, cool. Okay. His name is Norbert Wiener, and funny name, right? Basically, he lived some time ago in the century, and he's considered by many to be like the father of whatever of robotics. And he was basically a mathematician, but his whole thing was always like, build things that change. Don't build things that do the same stuff every time. And I just love this picture because it's like an old school robot with vacuum tubes. There's a bunch of math in the background that's clearly staged, and he's smoking a cigar. I really wish I had a cool photo like this with my research. But anyway, he invented a term called cybernetics. So if you ever wondered where does the word cyber come from, it comes from Norbert Wiener. So basically, the reason why you have Cyber Monday, or why it's called that, is because of this guy, okay? And he was a mathematician. But his whole thing was like robotics and a bunch of other things. And so that's what we're going to talk about today. If Robert Wiener, I think, if he lived today, I think he would say something like, hey, fam, instead of like doing a bunch of this stuff over and over and hoping that it leads to different outcomes, why don't you change what you're doing? And one way to change it would be to possibly measure something, okay? Like measure what the outcome is of the thing that you built, and then if you like it, keep it, but if you don't like it, adapt, change what you're doing, right? It's like a robot, right? A robot doesn't do the same thing every time. It does something different, the lights are on or off or whatever. And that's kind of a strange concept, but basically in water resources, the fancy term for that is called adaptive management. But as much as people talk about it, it's still not like a big topic. And the way that we look at it in our lab, in our research group, is through the lens of technology. Again, inspired by robots and other things. So I think a lot of you have interacted with this stuff before. Smart homes and smart widgets are all over the place. They measure the temperature in your house. They sell your data to Google, and then they make you feel comfortable and maybe make some money off of it. Maybe another topic for another talk, but essentially this stuff is infiltrating our lives, and our question was always like, what's it doing for water, right? And so here's kind of an image that we put together some years ago of like, everybody's talking about smart cities, but what's that mean for water and specifically stormwater? So you could imagine a city that's covered in sensors. These are devices that measure stuff related to water. They measure soil moisture, they measure rainfall, they measure water levels in all these basins, they measure whatever, flow. And then what they do with those measurements is they actually adapt. They control things like valves and pumps and gates to basically change how that water is flowing. So as I move forward through this talk, the thing I want to evoke, like as you're kind of thinking through this, is think self-driving cars, but for water. Okay, that's what we always tell people. A thing that always changes what it's doing based on the input that it receives. And so we set out to kind of build this stuff, and that's what we're going to talk about. So the first component we're going to talk about is the measurement part, and the second component we're going to talk about is the how do you change stuff part. So how do you measure water systems, in particular stormwater systems? So some years ago, we created this project called OpenStorm. And what we did is we basically created an open source project that shows people how to measure water systems. And what I'll do is I'll pass around what we affectionately call our sensor node, okay? And it basically is a device. Think cell phone, okay? It's just a cell phone. I'll pass this around. You guys can look around in it. it's a cell phone where you remove all the parts that you don't need for water. You remove the screen, you remove all the bells and whistles, and you're left with just a cell phone modem and the ability to plug in a bunch of stuff. So we plug in sensors that measure rainfall, sensors that measure water level, sensors that measure soil moisture, and then we put these throughout a city. So we could put like 100 of these throughout a city. They're connected wirelessly, and they send data to the internet, okay? And then what they do is they also control stuff, and I'll get to that in a second. So here's pictures of the students deploying the stuff. This is just some close-up of the sensors. This one they're deploying on a lake nearby. And this is what they look like. It turns out, actually, if you were to start walking throughout Ann Arbor, you'll see our stuff, because we have a bunch of these things that people from the county call, they look like bird feeders, so they kind of started calling them that. But they're little boxes that measure things like water level. They're deployed across bridges and a bunch of other things, and they're everywhere. We're up to, I don't know, in Southeast Michigan, probably easily to 150 sensors, maybe more. All I know is that my cell phone bill at the end of the month was really kind of expensive. Okay? But they're everywhere, okay? Because once you measure, you start getting real-time insights about what's happening. You don't have to come back 50 years from now and say, like, my infrastructure isn't performing. No, like, once this is connected, you basically look on the internet and you see how it's performing. Like, you see, is it working the way it's supposed to? Do I need to change what it's doing? And it's kind of at the, kind of like whatever's happening in smart homes, it is happening now in the, in your hand on a cell phone here. You're watching this data. And cities use this data for a variety of things. They check, like when they work with us, they check how well their infrastructure is performing. They check if they need to go maintain something. Anyway, it allows them to give this like big system level view of what's happening in their system. So that's step one, measure. We build lots of widgets to measure water across a city. Then we want to control it. So how would you control water in a city? If I told you, here's Ann Arbor, here's, let's say 50 square miles, what would you control water with? Any ideas? My mind. I like that one. That's good. I wish we could have that, but maybe once VR comes through, we'll get there. That's pretty cool. I like it. Anything else? It's really simple. It's existed for like hundreds of years, maybe millennia. Yeah. Valves, dams. There it is. Okay. So that's what we thought. Like, why don't we build valves and control stuff? Okay, where do we get a valve? Home Depot, or like Amazon. Okay, that's literally where we bought it. And we primed it 2 days, it was great. As you can see, it's not that expensive. But this is just a simple valve that goes up and down, but you connect stuff to it. So we go out, what you see in the background is a detention basin that's 5 million gallons of water. And don't ask me why, but the county and the city allowed us to install this and let a bunch of students control this. But what we attach to it is a thing. It is the thing that opens and closes it. You push a button on your computer and it goes, right? It's connected to the cloud, okay? And this is what it looks like. Here's a bunch of students doing it. This is Gerardo. He was actually in a community college when we were first doing this, and now he's finishing his mechanical engineering degree here. But we build these things, and we open and close the valves to basically change when water comes out. Okay, and you do it for very, very cheap. Like that whole setup right there, fully solar powered, a couple $1,000s. It's not really that expensive, right? And this is what the fancier version looks like. We don't buy them on Amazon anymore because we wanted to be taken a little bit more seriously. So even though it takes longer to ship. But anyway, this is a site near Whole Foods. This is called County Farm Park. Have you guys ever been to it? It's pretty cool. It's got a great playground, which is basically my day-to-day now, is to take my kid there. But it was like, ooh, we should control this. And so what it is, it's just one of those buckets that I was telling you about. It's a bucket that's sitting there. Water comes in and goes out. And what happened at that site is it just had a small outlet, right? It's a 12-inch outlet, and that water flows through, and you're supposed to slow that water down, right? That's what I was talking about earlier. But what we do is we come in and we connect this valve. It's connected to the internet. Now we can push buttons to either completely open it so it looks like the thing on the left, or completely close it so it looks like the thing on the right. So through the push of a button, you're reprogramming infrastructure, which is really kind of wild, right? Like you're completely changing how millions of gallons of water flow, and all these benefits all of a sudden start accruing. So it turns out that with water, if you hold it in one of these little like mini lakes, like a basin, if you give it time to settle after a storm, all these sediments will fall out. And sediments in the Great Lakes carry nutrients, and nutrients drive algal blooms, et cetera, et cetera. And so this wetland over here is effectively treating the water. There's bacteria and a bunch of other stuff that's treating it. And then we just look at the weather forecast and we say, okay, Weather Underground is saying it's about to rain. You just open the valve and let the water out. And then you have storage for the next storm. Okay? And where that becomes really interesting is when you have hundreds of these, okay? Or in this conceptual example, what if I have 2 valves? So let's imagine we have a neighborhood downstream. So this is a neighborhood that regularly floods, which exists in Ann Arbor. And then we have 2 neighborhoods upstream that are feeding water down it. So usually when it rains, the water levels downstream go up and they go down and they flood. So you imagine if you had 2 valves on there now, that changes things completely, right? So if it's raining a lot in one neighborhood, and it's not raining a lot in another part of the neighborhood, then you could maybe hold water in the part that has storage and release it in the other one, and all of a sudden you're controlling multiple neighborhoods across the scale of a whole city, right? You're going from that orange thing to the blue thing, but you're doing it at the scale of the whole city, not just the scale of the individual site. And so we wanted to build this, and that's what we did. So for those of you who ever want to see this, we do tours of this. This is Arbor. This is the watershed that contains Costco, and basically 10 square miles. We didn't know how many sensors we needed, and we had funding for it, so we just put a ton of sensors. And they measure everything from water levels, water flow, water quality, like a ton of stuff. It just became this big test bed, and then we also put these valves in it. And we were able to start controlling this 10 square miles to do stuff. And what are the kind of things we can do? So here's one of the sites that we're controlling. So I'll show you kind of, this will capture how the system typically works and then what control can do to it. So here's that basin that we're controlling. It's 5 million gallons, and we put a valve on it. We went to Amazon, we put a valve on it, connected it to the internet. But before we did that, what would happen is it rains all over this neighborhood. This is about 2-3 square miles. And what will happen is the water from this basin will flow downstream to this location that would typically experience flooding. And this location was actually built by the city of Ann Arbor to treat the water before it goes to the Huron River. So at the outlet of this wetland is the Huron River. And the way that the system is designed is all this water is supposed to flow through here, flow through this basin, go through this wetland, and then this wetland is going to treat it. That's why it looks like a snake. You're slowing it down, you're treating it, and then cleaner water goes through the river. Problem is, despite like $3-4 million of investment, these things are never big enough. You build a small bucket, it cannot hold all your water. And so what you see most of the time is this kind of overflow scenario where all this treatment capacity is bypassed and you get this little bit of a, I wouldn't call this localized flooding because it's designed to basically flood. It's designed to flow over, but you're bypassing all this capacity. So what we try to do is basically say, well, could we control this? Could we just put a sensor downstream, right, that's measuring the levels in that wetland and only send down water when it has capacity, right? So we're controlling the valve upstream and only sending water down when there's room. I mean, it's not like an earth-shattering concept. You're just opening a valve when somebody's telling you they got space, right? But again, it's across the span of a couple square miles, and it's a bunch of students doing it. So this is what's happening. So this was in November, one of the years that we did this experiment. This is that 5 million gallon basin that we put into place. And essentially, when that place downstream is ready to take the water, we open up the valve downstream. So what I'm showing you here is the water level in both those things. The upstream basin, which basically when you open up a water valve, the levels go down. And then about an hour and a half later, those levels start changing in the downstream wetland. And here we have that. So here's the wetland, and you can see the levels are changing from that red location to the green location. And because it's not raining, we know that the only thing that's changing those levels is the actual control that we're carrying out, okay? Which is pretty exciting. Again, it's done through a bunch of open source hardware and a bunch of students playing around with the permission. But basically, it was really exciting to us because it showed us that control impacts the whole entire place. It doesn't just impact your local location right there. And that's when things kind of picked up. The reason, if you're wondering, like, why do we have videos? Yes, videos are cool, and we want to buy GoPros. But when we first started doing this, like, this didn't really exist in the water community. It's only some people kind of even accepted it as a fringe thing. And they didn't believe us. When we started doing stuff, they're like, this sounds complicated. What are you guys doing? And we actually had to start taking videos so people would take us more seriously. So it wasn't for us. It was just that it wasn't, even though it seems obvious now, maybe it wasn't a really established concept. What are the things that happened from this? This went to the city and the county, and they started doing some calculations on how much money it started saving them. And that's when the research kind of started becoming a little bit more serious, because they basically said, we can build these things way smaller now because you're telling me you can keep water upstream, okay? And there's all these benefits here that we don't have to go into. They're like basically, how much dollars you pay per gallon of stormwater and nutrient savings and stuff. But essentially what they calculated is that this one valve that we installed saved them about $1 million. And that valve cost, the valve cost us, when I put it all together, like, let's say $5,000, but it didn't, okay? So comparing to building a new site, which cost many millions, just adding one valve apparently gave them the savings. I stay away from making savings calculations because I try to provide just academic assessments, but nonetheless, that was kind of cool. So this is an image that we always kind of show. It's kind of an interesting one. This is, again, that whole watershed, 10 square miles. And after we did this demo, we were nudging the students and saying, like, what are you going to do now? So what's being plotted here is the flow of water at the outlet of the watershed, right near the Huron River. And what they did is they controlled this watershed to spell the Michigan M in the water levels, okay? So it's totally obscene, and it's kind of a little bit funny, potentially. But remember, you either get a spiky water flow or you get a flat one. by controlling it, you can start drawing things. You can draw letters or worse things basically in the hydrograph. And this is an image from a federal station that's measuring this. And we get contacted by people saying, like, what is happening in this watershed? And people are practicing. Now, it seems silly to spell letters, but when you give this to somebody who actually works on water, when they realize they can spell letters, they can start doing much more meaningful things, right? And the level of precision you can achieve with this is really just kind of crazy, because you can do a different thing during every different storm event, just like Norbert Wiener would have loved us to do. And so what our group does is we essentially try to take a century or more of knowledge about water systems, as we've been studying them for a very long time, and we try to embed it into a new generation of like algorithms that control water. So when you think about all those techies out there who are telling self-driving cars how to drive, we're kind of trying to do that for water. Usually when I give these talks, I give a ton of math, but today I'm not. So anyway, just imagine that this arrow is like a tremendous amount of math, and if you want to see it, come talk to me, because it's actually really exciting. So, can you go bigger, right? 10 square miles is cool. Can I go bigger? And we always say yes when people ask us, so this is free. So here's the city of Detroit. Okay, we're gonna zoom in, we're gonna bypass Ann Arbor, and we're gonna go to Detroit, and we're actually gonna look a little bit wider. We're gonna look at the Great Lakes Water Authority, which is basically what's known as a combined sewer system. All those little blue lines is stormwater and wastewater that feeds through this intricately complex system that's been really truly built over the span of a century through a number of really kind of crazy things. These are like large basins, so think big buckets basically that feed water throughout the system and pass water between each other, and effectively, once it's all done, it ends up in what is basically America's largest wastewater treatment plant, okay? It's a place where all your wastewater goes and is being treated before going to the Detroit River, and it is truly huge. It's one of the largest in the world, okay? And you can go on public tours of these if you're interested. It's really cool. But essentially, this was kind of an opportunity, because once we started talking to them, they told us, look, there's a lot of challenges in Detroit, right? We have issues with these sewer overflows. When it rains a lot, the bucket's not big enough, so everything overflows. But we do have a lot of sensors. We have a bunch of sensors that are measuring flow and level and a bunch of other things, and our operators, the people who sit in this command center, and this command center is like incredible, like that's also worth the tour. They basically push buttons and turn knobs to tell that water where to go. And one way to tell water where to go is to just take a giant sewer pipe and put into it like an inflatable pillow, like a dam. So here's one, like you can see it inflating. This is a 30-foot sewer, okay? Not that you would walk in one ever, because you never see these things. But it's 30 feet, and when they push a button, this thing opens and closes. I think the company that made this was like one of the tire companies, like Bridgestone or something like that, right? I mean, who do you go to make a giant inflatable sewer dam? What we essentially did for them is we took a lot of their sensor data, and I'm bypassing a tremendous amount of math again, and built like a dashboard for the operators, basically saying there's no way you're ever going to be able to look at 100 sensor feeds at the same time and turn knobs and turn stuff on and off. Instead, let us take in all that data and do some fancy data processing, machine learning, whatever you want to call it, okay? And we can talk about that after class. And what this dashboard will provide you on your computer is just recommendations like turn that pump on, turn that pump off, and do it dynamically, right? Change it during every given storm. And the results that we got through simulation here were pretty staggering. They gave us this project. They funded us about I think it was like $140,000, which just sounds like a lot, and it is a lot of money. But they basically said, hey, U of M, here's that money. Tell us if we can reprogram our system. And we showed that just one part of the smaller system, if reprogrammed, if you will, can reduce sewer overflows by 100 million gallons. That's a lot of water, 100 million gallons. They're looking at having to build a big bucket, and their big bucket costs, for 100 million gallons, $500 million, okay? Like, that was a pretty wild discovery, because it basically says, before you dig, before you build, why not see what you have? And as the drain commissioner here, the water resource commissioner always says to me, tell me what I can squeeze out of my system. Can I squeeze more performance out of it? And the news is, you can squeeze more out of it by reprogramming it, which is kind of interesting, right? And so that's what we've been working on. And I guess the question to that would be, does it get, is it scalier? Does it get bigger? And yes, it gets bigger. So you guys are sitting inside the Huron River watershed. This is 800 square miles of land that's a big bowl, and when water flows into it, it goes through the Huron River. Have any of you ever tubed in the Huron River? Yeah, it's pretty cool. It's actually one of the cleanest rivers in Michigan, because there's a lot of organizations working here together. But there's, Ann Arbor is right in the middle, so if I use my fancy pointer that I'm really just disappointed I paid $100 for, Ann Arbor is right here, okay, in the middle. There are 17 reservoirs, believe it or not, 17 giant reservoirs in this watershed. And when we started working with them, there were only 3 measurements or 4 measurements of water flow. And no matter who you are, even if you're like super advanced mathematician, controlling 17 things with 3 measurements doesn't make sense, which explains why you would flush out fish, why you would flood things, why all sorts of stuff happens. So what we've been doing with them is basically putting in all these like cheap measurements of water flow, and now the reservoir operators are using it. So essentially going from 10 square miles to Detroit size, 2 giant regions, and this is where we are today. So I'm happy to report after summer of 2019, our like open source widgets in partnership with tons of different people and people who pay for it, like organizations that pay for it, are basically covered almost Southeast Michigan in sensors. So all those markers on our map have been deployed by graduate students and undergrads in our lab in partnership with them. And I think it's really kind of building a foundation for what could be called, or at least I think about it this way, as a water information system. So that thing about building something and hoping it works, now we can build it and we can check that it's working. We can check that it's working across massive regions. So this is a live thing, and we're gonna share all these data are basically available. It's really cool. So again, kind of summarizing, if you have something, you want to do something, which is how we do stuff now, you may want to consider some feedback. You may want to measure, and before you dig, kind of see what more I can squeeze out. And that's kind of the summary of our research as we do it. And what I wanted to show you is just a couple of closing things to bring you to the next speakers. The person coming next time, Ram, he works on self-driving cars. And I was talking to him, and he's going to tell us about self-driving cars. I told him, hey, Ram, do you guys have windshield wipers in your cars where you're actually logging if they're measuring stuff? Because we don't have rain information. We have not a lot of rain gauges for the regions that we work at. So kind of like this is my image of this is the silliest image of a windshield wiper I could find on the internet. I think all it's missing is the googly eyes. But basically, the idea was if you have a fancy new connected vehicle that's driving around Ann Arbor, and we have 180 of them or something like that, could they be logging their windshield wiper information? And he was like, yeah, they actually are. So here's a camera on one of the vehicles, and you can see the windshield wipers turning on every time it's raining, and we can get that information, and we can basically start making brand new rain maps. Okay, so what you see on top is what we think is happening with rain, and on the bottom, what we think is happening when the car is driving around. So those little dots are driving around. They're collecting rain information, and what we're basically seeing is that in a lot of places, there's rain where we never thought there was rain, and vice versa. And so basically, we don't need to deploy more sensors. In some cases, we can actually use data that's already available. So this is kind of just the windshield wipery water thing, but it just shows you like different applications for these technologies. Again, our lab uses a lot of like techie stuff to look at water problems, and I think Ram might talk about this a little bit. I just want to close on this one. We don't just work on stormwater, we actually work on drinking water. So Ernesto is in here. Where's Ernesto? Oh, there's Ernesto. He just came back 8 months in Mexico City, right? Deploying sensors on people's taps. So visiting families in their homes, putting water quality units at the tap, essentially, at the connection where the water comes into the house to measure what happens with water. And we have a really cool project coming out right now with Professor Raskin. She's leading this Blue Sky project where we're going to try to do this in Ann Arbor too. So soon we're going to have tap water in Ann Arbor instrumented to see what happens across these large systems. Because currently we don't measure them in people's homes at these kind of resolutions. And again, we can talk more about that after this. And so I'll just close with this. I'll show you the group of students who built this, because I'm proud of the fact that this was put together by a bunch of people who are still in their training, but they're building things that I feel like really haven't existed before. So I'm pretty stoked about that. And I'll leave it at that. And I think I have 10 minutes for questions, so go. Okay, so we'll take questions. We got one right there, yeah.
So I'm computer science.
Yep.
One of the things that my advisor in undergrad would never stop harping on about is how ridiculous the Internet of Things is in terms of computer security.
Yeah.
And so as soon as you start mentioning all like Internet of Things kind of devices that you're using,
yeah.
That was the first thing that came to mind. Is this how do you deal with the security threats? How do you deal with the computer security?
Yeah, so the question is about security, and I appreciate your the technical wording of it, because usually when I give these talks, especially in public, the way that question is worded is very short. What about security? Okay, and the answer to it is absolutely. It's something you have to keep in mind. Like I think it was just a year or two ago that all those internet-connected toasters and juice machines and whatever brought down the internet. Okay, so yeah, that could happen. Could a system like this be exposed to somebody who wants to do damage? Absolutely. And we do our best to take the sort of modern precautions. So like what I always tell people is whatever they're doing at a bank, we try to do that. We encrypt the data. We We make sure that we basically have all these things up that protect it. We have authentications and all these different things. Nonetheless, no system is fail-safe. And what's interesting about it is you kind of have to weigh the pros and the cons. And that's what it really boils down to it. What city is going to adopt this? Are the pros of saving a ton of money going to outweigh, or having environmental benefits or reducing flooding are going to outweigh this thing? Because everything that's connected is under threat in that way. What I will say, though, is we have clogged pipes right now. We have pipes exploding. We have no clue what's happening. So in some way, by connecting, at least you'll know what's happening. And at least this is our thing. But I wish I had a good answer for you, and we can go into the technical aspects of what layers of security we use. But at the end, things that are connected are vulnerable, and that's something we have to contend with. So smart cities are going to be open to new kind of vulnerabilities, but new benefits as well. Yeah. Giant rant answer. Yeah.
What kind of research have you guys done in terms of like how it affects like environment, like the species and everything like that?
Yeah, that's a great question. So question is like, are there, if I can rephrase, are there environmental benefits to these technologies? Because oftentimes flooding is the first one that kind of comes to mind. It's the one that we easily talk about, that's accessible. Absolutely. There are really big environmental benefits, and we're actually working in a lot of these cases with ecologists and biologists and other people who look at what happens when you change the flow of the water. When you're spelling that M, does that kill fish, or is that good for fish? Stuff like that. The answer is that you can create flows of water that are actually quite beneficial for these systems, and that's what we're doing through collaboration. It's not my area of expertise, but we do measure a ton of it, and that's a new area that we're getting into right now. And I do think actually it's kind of interesting because during small storms, you'll be able to control for water quality, and during large storms, you control for flooding. And you can't do that with regular infrastructure. You can't flip a switch and change it, right? So multiple benefits. Yep.
Have you thought about taking even more of a micro approach, understanding that some houses may have rain barrels?
Yeah. So the question is basically, can you control many smaller things, like big bucket, small bucket, right? We went for medium buckets here, basically. When we started the project, the way we actually sold it to the funding agency, it's the Great Lakes Protection Fund. It's a regional foundation that funds environmental research. I never thought it would get funded because I thought it was weird and sci-fi. But basically, we said rain barrels. We're going to go in everybody's backyard, and we're going to control their rain barrels. And then when we got funded, I did the math on the rain barrels, and it just was like you'd have to control every rain barrel, and still you'd get flooding. So some things are small. But the good news is we actually made these rain barrels, and you can put one in your house. I think it's on our website. It has a soil moisture sensor, and what it'll do is basically it'll water your plants for you when they need it, and then it checks the weather forecast and does the one thing that homeowners don't do, which is drain their rain barrel ahead of time, right? So it has those things implemented. It's more of an educational tool for us than it is like a large-scale impact, but it kind of sells the idea, right? Good. There very well could be. So the question was, are there negative impacts to some of this? I think as an engineer, I've learned over time that you never say that you have the right solution. Because every time you build something that's good, it's going to have drawbacks. Just like we talked about earlier. Putting a bunch of little good things is going to be good, and then there's a bad example, right? There probably is. I don't think there's anything that is just the solution, that's how you should do it. There's always going to be unintended consequences. The thing I like about this, though, is you can change it. Again, you can flip the switch and oh, we messed this up, let's not do that again, right? With infrastructure, you got to wait 10, 20 years before you dig something up again. So there probably are. I don't know what they are, but we'll find them. Yeah.
Have you heard from any cities outside of Michigan about them adopting this kind of technology?
Yeah, so the question was, I'm repeating your questions because it's being recorded. Are there other cities doing this stuff? There are some examples. So if you go to Europe, the Netherlands are man, they're doing stuff. They're underwater, so they have to look towards all sorts of solutions. So they have giant gates and stuff and monitoring for tide and all this other stuff. Spain has a giant system they're controlling in Barcelona. That's really cool. That's fun part about this job, too. You get to go see stuff like that. By the way, Paris Sewer Museum, awesome. But anyway, most locally here, South Bend. So South Bend, Indiana, which we're going to have the chief innovation officer. We're just trying to drill down the final date with him. He's going to talk about it. And some of those things have turned into companies. So there are companies offering these services right now. We're more on the research side. Yeah, it's growing adoption. I'd say in Southeast Michigan, it's primarily us or in Michigan because we're going around preaching it or whatever. But there are cities that are looking toward, but the adoption barriers are huge. Right? Because when a city floods, it just floods. And you can't really sue them because actually by law, there's things called act of God. You know, we talked about this yesterday during our workshop. When something floods, a lawyer can say for the city, that's an act of God. Like, we can't protect against everything. When you install a valve, if you mess something up, it's not act of God, it's your valve. And so a city, you know, they got to do a million different things. And last thing they need is a researcher coming in and saying, like, you guys got to put valves everywhere. So I think we're going to hear from them throughout this series about how they view technology. Because they got to solve day-to-day problems, and they might not nearly think, you know, widgets are nearly as cool as I think. So, but it's slowly growing. It's definitely not the common thing, though. I'll get back to you in a second. Yep.
Your system informs, I guess, how builders develop new plots of land, so that vertical services cost or
Yeah. Yeah, so would having a valve like this change how developers develop stuff like malls? Well, I guess malls are kind of going downhill now, but like other things. What we showed with this is that you can build one of those detention ponds at half the size and get the same benefits. And I can tell you the developers love that because that's more parking lot, that's more buildings, that's more other stuff, and all they got to do is pay for a valve. So it started off a lot of conversations. We did interviews across the country, and that was one of the main takeaways. Like, developers love it because of money, and maybe that's an adoption, you know, mechanism. You had a question?
Yeah, kind of to your earlier point about cities like determining what is an afterthought and what isn't.
Yeah. Yeah. Some places are risk averse. So going back to the act of God question, like, what do we have to do to get this stuff approved? Sometimes we show up in a city and they're like, great, let's put sensors everywhere. You know, technically we're bringing in research funding, so we're paying for it, and they're open to it. But 9 out of 10 places, they're like, shoo. Like, literally, like, get out of there. And we have to have so many coffees with so many people. And we just happen to be so lucky to be located in the place where they said it's just allowable, right? Because they are taking on a risk by putting this in place. And it has happened. Like, homeowners will call in and they see one of these detention basins and they're like, they call the city and they're like, guys, it's clogged. You need to fix it. And the city's like, no, that's University of Michigan. They're holding water, right? So I don't know if there's any architects or landscape architects or planners here. We're changing how water looks. And that's freaking some people out, and some people are okay with it. But it's fundamentally changing how people experience their urban environment, which as an engineer, I had zero appreciation for because I was always optimizing. I was like, do this better, better, better. And then somebody said, like, your thing is clogged. And it's like, it's not clogged, but man, I'm not doing a good job like thinking about how people perceive this. And so we're actually collaborating with social scientists and a bunch of other people who are asking people how they